Meet friction, the force that everyone seems to hate. And I think friction gets such a bad rap because, well, friction likes to, it likes to steal energy. But I think friction might be a little bit misunderstood because as much as it can be taking away energy, nothing really would be able to get going without a little bit of help from friction. So in this lesson, let's take a closer look at friction. All right, so to start looking at friction, let's look at our definition. It is a force between surfaces that is going to resist movement. Okay, let's take a closer look for what that means. So let's say we have an object on a surface and someone's going to come in and try and push it. Once we get it moving in this direction, friction is going to come in and push it in the opposite direction. It's going to resist it trying to move, and it's going to try and slow that object down. And even if this person thought, okay, well, friction's pushing in this direction, let me go to the other side. I'm going to push it this way with friction. Well, sneaky little friction is going to go to the other side and resist movement in that way. So whatever direction the object is moving, friction is going to push in the opposite direction to slow it down and resist its motion. And that's why we might not like friction, but remember that it's also helping this person push because it's actually applying the force that is allowing their feet to grip on the ground so they can push in that direction and not just slip. And even their hands on the box would probably slide up or slide down if there wasn't some friction keeping it there. So every step, tire, brake, even nail and screw require friction, and so much of the world would just fall apart without it, like a house of cards collapsing. So as much as friction can be annoying, it's also very useful for having the means to get anything going. So what causes friction? Let's consider this scenario with a wooden box on like a concrete floor. And I'm going to give the box a push and it's going to slide for a little bit, but then come to a stop because these surfaces are pretty grippy and friction is going to be pretty high between these two surfaces. So what's going to make the friction higher in this? Well, they're pretty rough surfaces. And if we zoom in even further, we can see that they are very rough surfaces. Even things that might appear pretty smooth, when you zoom in on them, they become quite rough. And these surfaces would probably be kind of the most rough surfaces. And we can see if you try and slide them against each other, there's lots of things that could crash into each other. But even points where the atoms of one material are closer to the other, there can be some attraction between the atoms, and that's going to resist moving or resist sliding past. So there's a whole bunch of points here that just kind of covered on the surface where we're going to have some frictional force resisting the movement in that direction. Again, that's what friction does, resists movement. Let's go to a different surface now. Let's go to ice. I'm going to do the same thing. I'm going to take this box and I'm going to push it to the side, and it's going to slide a lot further right off the screen because there's not as much friction on the ice surface. So we're going to zoom in on the ice and notice that it's not perfectly smooth. There's some bumps, but it's much smoother than the concrete was. So if we try and slide the wood against it, it's going to be a lot easier to do so, and there's a lot less points that are going to be resisting that movement. And actually with ice, one thing that makes it even more slippery is once we do get some friction on there, friction loses energy to heat. Loses energy to heat, you can probably feel it in your hands if you do that, and that's going to melt the ice just a tiny little bit. When it melts the ice, that's even going to fill in those gaps up there, so there's even less friction on those. So ice is a really slippery surface because they actually get a thin layer of water, which things slide really well on. So we know what it is, what causes it. Now we're going to look at how to calculate friction. So we have the symbol here, FF, for our force of friction. And we have to consider two things. We have to consider that grippiness that we were talking about, but then we also have to consider the pressure between the surfaces and how much they're being pushed together. So how much they're being pushed together, most people kind of assume it has to do with gravity, how much it's pulling it down onto that surface. And that's a good place to start, but remember that the pressure between the surfaces or from the surface is actually called the normal force. Now in that picture up there, we can see that they're probably the same number. And in many cases, gravity and normal force are the same if you just have a mass resting on a surface. But sometimes we're pushing down on the object, pushing up on it, or maybe something's in free fall, The force we should focus on is the normal force, because that's the pressure between those surfaces. To take a look at why that is, let's take a look at this example. So here I have two wooden blocks sitting on each other on a piece of concrete. We won't worry about the concrete right now, but the two wooden blocks are on top of each other. Gravity's pulling down, normal force pushing up, so there's some friction between each other. Okay, and in case you're thinking, well, I could use normal force or gravitational force, what I want to show here is what if we got rid of the normal force? Would the gravitational force describe how much friction there is? So what we're going to do here is I'm going to keep gravity, but I'm going to get rid of what these blocks are sitting on, and it's just like we're going to drop the two blocks. And now they're falling through the air. These two blocks are falling as the wind is rushing up. And you can see they can just slide on top of each other because there's nothing pushing these two blocks together. It's like they're both in free fall. So what this is meant to show is that even though we have gravity, if there's no pressure between the surfaces, no normal force, there isn't going to be friction. So what we have to take into account is the normal force. So hopefully that helps you kind of understand that. Let's put it into a formula now. If I increase the normal force, I'm going to get more friction. And if I increase the roughness or the grippiness between the surfaces, I'm going to increase the force of friction. So we're just going to multiply these two things. The first thing, force of friction is equal to the normal force multiplied by the grippiness. Now, grippiness isn't necessarily the most scientific word, so they called it the coefficient of friction. And we got this symbol that's kind of like a U. It's also got a little tail on there. I'll try and draw it in kind of like this. It's a Greek symbol that is going to represent our coefficient of friction, but most teachers are okay if you just end up writing it U. And that's all we have. That's the entire formula for the force of friction. Let's take a look at an example for how we could use that. Okay, so this example reads, an athlete pushes a 50 kilogram weighted sled with a force of 260 newtons, and the sled is going to accelerate 0.65 meters per second squared. It's asking you for the coefficient of friction. Okay, so how do we start this question? Well, if it's asking for the coefficient of friction, as we just said, I just introduced a formula with the coefficient of friction, and we've never seen that symbol before, so we're going to need that formula. The only formula with the coefficient of friction, FF is equal to Fn times mu. Perfect, so we just need FF and we need Fn. So looking at the scenario, we don't know FF and we don't know Fn. We don't know either of these, so not much that we can do off the hop, but we do know that we just need to figure out those two forces. So let's start with the first one, the frictional force. How could we figure out the frictional force? Well, look at our picture, and as we've been doing pretty much the whole time in this chapter, is draw a free body diagram, F nets a sum of the forces. So free body diagram, we're going to include friction. That's going to be in the x-plane because friction is going to go that way. They're applying a force this way, so let's put those two forces on there. And there's nothing else pushing side to side. Those are our two. So F net's the sum of the forces. F net is the sum of FF and FA. Now I want to solve for that FF. So what do I know? Well, let's start over here with F net. I can solve that because remember F net is equal to mass times acceleration. So I can get that number, and force applied, it did tell me 260 newtons. Let's plug in our values there. 260 and MA, plug in mass and acceleration, so 50 kilograms times 0.65 meters per second is the acceleration. And I end up getting 32.5 over here for the net force and an applied force of 260. So that means if the overall force is just 32.5 and we're applying 260, friction's taking away a lot because it's pushing in the opposite direction. So how do I solve for that? I'm going to minus the 260 over to this side, and we get negative 227.5. Friction has a force in the opposite direction of 227.5. So there we go. We now have the frictional force, and we can move on to solving for the normal force. Normal force is pretty similar, just now instead of looking in x, we're looking in up and down in y, because that's the direction the normal force is going, straight up in the air. So to put our forces there, we have Fg going down and Fn going up. So let's write our formula. F net is Fg plus Fn. We can figure out Fg with mass times gravity, so let's do that just down here. 50 times 9.81, and we get negative 490.5. I'm going to call negative downwards. Okay. We can put that in, and the overall net force, mass times acceleration, is 0. Now, that can throw some people off because you think, well, don't we have an acceleration of 0.65 meters per second squared? Again, that was in the horizontal direction. This mass is not accelerating up or down, so acceleration in this plane is going to be 0. Okay, it's overall balanced. Our gravity is balanced out by the normal force in this scenario. So what's that make Fn? Fn is just going to be the positive 490.5. We can sub that in there, and now we have our two values that we're looking for to solve for the coefficient. So last step, let's just take that 490, divide it here, the 227.5, divided by 490, and we get negative 0.46 as our coefficient of friction. But just before you circle your answer on a test or an assignment, it may give you the option for a positive 0.46, and that actually is the correct answer. Even though in this calculation you got a negative, the correct answer is a positive. Why is that? Well, the negative was just indicating direction. We said that way was negative, this way was positive. Can the coefficient of friction have a direction? No, it always resists movement. So if I push it this way, friction is going to come here. If I push it this way, friction is going to come here. So friction doesn't have a set direction. So its coefficient is considered directionless and unitless. It's just a number of 0.46. So just keep it as a positive, non-directional answer. Okay, so we know what friction is, what causes it, how to do calculations. The last part is to consider static versus kinetic friction. Static means stopped. So if I apply a force to a stopped object, it's not going to move because friction is keeping it in that position. Static friction is a little bit weird because it can actually change. If I apply a force this direction of 5, it's going to keep the box stopped, so it's going to apply a force of negative 5. Even if I applied a force of 1, it's going to push back with 1. It's always going to match what I'm going to do. So let's put up another number. I'm going to push with 8. Friction is going to push back with 8 because it just has to match whatever I'm pushing with. It can never be higher than the amount we're pushing with. It's just going to keep it stopped. But there is a maximum amount. There's only so much friction it can have. So now I'm going to increase it to 10 newtons, and it's going to push back with 9. And in this case, that's its maximum amount of friction that it can push back with. So in this case, I'm pushing with more than friction. It should break free and start to slide this way. So let's see it go. It slides in this direction. But wait a second, the friction changed. The amount that it was pushing back on used to be 9, as we can see over there, but now it's going to negative 8. So what it's saying is when it's sliding, the frictional force is actually a little bit less. And this is true. This is called kinetic friction. And when surfaces are already sliding past each other, the coefficient of friction goes down just a little bit. So kinetic friction is when it's moving, static friction when it's stopped, and kinetic's always going to be a little bit less than the maximum static friction value. So that's our last little complication. Let's see how it could apply to a question. We have a big question here. A student is trying to move their 40-kilogram desk in their room, and the static coefficient of friction with the floor is 0.85. The kinetic is 0.72, see it's a little bit smaller. What amount of force does the student have to apply to get it moving, and what will it accelerate at once it's moving? So kind of two questions involved here. Let's start with the first one. How much do you have to push with to get it moving? Okay, so we'll start with our free body diagram here. We're going to apply a force this way. Friction is going to apply a force that way. To get the concept, let's just imagine the maximum static friction was 100 newtons. If I push with 20, it pushes back with 20. If I push back with 50, it pushes back with 50. The point they're going to have to get to start it moving is that maximum amount of static friction. If I go 0.001 over that, I'm going to start accelerating it forwards. So we're trying to find the maximum amount of static friction, and that's the amount that I have to apply, because as soon as I go over that, it's going to be accelerating. So I'm just going to write here that my force of friction has to equal the force applied. I have to match that maximum amount of static friction. Okay, so to find FA, I'm going to have to plug in for FF. The FF formula is Fn times mu. Now, when we look at the free body diagram, the Fn is up, Fg is down, similar to what we had before. And I'm going to kind of skip a step here from the diagram. I'm going to say, since there's only two forces and the desk is not accelerating up or down, those have to be the same. Fn has to be the same as Fg because there are only two forces and it's not accelerating up or down. So I know that my normal force is Fg. How do I calculate Fg? With mass times gravity. So I'm going to put into the equation mass times gravity times coefficient as my formula for friction in this case. And most teachers should probably be okay with that. if you've identified this scenario. Now I can plug my numbers in, my mass times gravity times my coefficient of static friction, because I'm trying to start it moving. It stopped right now. And I get a value of 333.54 newtons is the amount of force I have to apply to overcome that static friction. So let's just round it to 3.3 times 10 to the 2 newtons. That'd be my final answer for part 1. Now looking at part 2, it says what will accelerate at if you keep applying this force. I'm looking for acceleration. I need F net. All right, F net is the sum of the forces. So F net's the sum of force of friction and force applied, again in this horizontal direction. I did put a negative there just to remind me that the friction should be the opposite direction as the applied force. They're pushing in opposite directions. Okay, let's see what I can plug in. Well, I know that F net is ma. It's good that I have the acceleration there because that's what I'm trying to solve for. My force of friction is mg mu, just as we did before. And I know the 333 is the force that I'm going to apply. We found from step 1, that's how much force I need to apply. And at this point, you might be thinking, well, wasn't the 333 the force of friction? So isn't it just going to be 0 acceleration? It would if kinetic friction was the same as static. But we're saying now that it's sliding, the frictional force is going to go down because my coefficient is a smaller number. So that's got to go in here for coefficient, and we're going to have a lower number for friction. So let's plug in some numbers here. We have, well, the arrow's going the wrong spot now, but to 0.72 over there, we can calculate our new amount of friction, and we're going to try and solve for this A, solve for the acceleration. Okay, so once I have this value here, I think I click to it. There we are. Negative 282.528 is now our frictional force with the 333. So we'll add that together and get a value for F net, and then we're going to divide 40 by that. So add these together, divide by 40, we should get an answer of 1.275, which would round to 1.3 meters per second squared. So we apply with this amount of force, it just breaks it loose, friction goes down, and it accelerates at 1.3 meters per second squared. Kind of tough questions, but I hope that helped you to understand what friction is, how it works, and how to apply it in static and kinetic scenarios. If you found this video helpful, check out the course playlist here, as we have lessons for entire courses of high school math and science that you may find useful as well. But that's all for this lesson, so thank you so much for watching, and I will see you in the next lesson.